This lesson is brought to you by SHAFTP Productions, Student Higgins Association for Teaching Physics. The learning objective that we will be covering today is 3.B.1.2 of circular motion. The student is able to design a plan to collect and analyze data for motion, static, constant, or accelerating, from force measurements, and carry out an analysis to determine the relationship between the net force and the vector sum of the individual forces. Alright, let's start the problem. An 830 kg race car can drive around an unbanked turn at maximum speed of 58 meters per second without slipping. The turn has a radius of curvature of 160 meters. Air flowing over the car's wings exert a downward pointing force called the downforce of 11,000 newtons on this car. Question A states, what is the coefficient of static friction between the track and the car's tires? To figure this out, let us first make a free body diagram. Here is the top view. The dot being the car, this arrow is F of n and symbolizes the normal force. This arrow is F of d, which means the downward force. And this arrow is F of g. Note that these arrows are not drawn to scale. Let us review the variables that we already know. V is equal to 58 meters per second. The mass of the car is 830 kgs. The radius is 160 meters. And we need to find the coefficient of friction. Let us make the equation for the net force. Net force is equal to force of friction, because this is the only horizontal force acting upon the car. All the other forces are vertical and cancel out. We also know that F of F is equal to mv squared over r, which is the equation for centripetal force. We also know that force of friction is equal to force normal times the static coefficient or kinetic coefficient of friction. F of n can also be stated as F of g, F of gravity, plus F of downforce. This can now be plugged into the equation Fg plus Fd times u is equal to mv squared over r. We now divide both sides by the quantity Fg plus Fd. Another way to state Fg is mg. When we plug in all the respective values for each of the variables in the problem, we get the coefficient of friction as 0.91. Let us now continue on to part B. Part B asks, what would be the maximum speed if no downforce acted on the car? So now let us draw another top view free body diagram on the car being this dot. F of n is equal to F of g in this case because there's no external force such as downforce provided into the car. We are trying to find out V. We know that mass of the car is still 830 kgs. We know the radius is still 160 meters. We know that the force of downforce or FD is 0 because it is non-existent. We know U, or the static of coefficient, from our previous problem to be 0.91. Let us plug this into the equation. Force centripetal equals mv squared over r. Again, we know that the net force is equal to force centripetal. So that's a way we can get to this equation. Force centripetal is again force of friction, which, as we knew from the previous problem, is force normal times the coefficient of static friction. And this is equal to mv squared over r. We are solving for v, so some simple steps should lead us to plugging in all the variables and solving for v in this equation gives us v equals 38 meters per second. And that's it.